second semester test review for the final. Question number 1 says, know how to calculate changes in frequency due to the Doppler effect. So first things first, probably ought to know what the Doppler effect equation is, and then talk about its different components. So the Doppler effect says F prime, meaning the new frequency or the observed frequency, will equal the original frequency, F, times this big old set of parentheses. Should be V, S, and D plus or minus VOBS, VOBS, all over VSND minus or plus the source. Okay, so first thing you need to do is be able to identify what the individual parts are. The F prime is the observed frequency after the Doppler effect has taken its impact. The F without the apostrophe is the frequency that's created by the source of the sound, or light if it was light. But here we're talking about sound. VSND is the velocity of sound. In the atmosphere here on Earth, the velocity of sound is 343 meters per second. But if it was through a different material like water or some other type of medium, the Doppler effect would be different there. Plus or minus, because we both have the option to go towards or away from a device, from the source or observer. And so that has a choice we have to make. The V observed is the observer, is the person listening to the sound moving. Okay, if they're moving, then there's a velocity there. On the bottom, VSND is again the sound, how fast does the sound travel, and then the V source is the source of the sound moving. Now I'm going to tell you up front, in this class, we're only going to work with one moving thing at a time. We're either going to let the observer move or we're going to let the source move and work the problem. So a really simple example of what this might look like, if I tell you that, say Eliza is running with a big stick in her hand. She's going to pole vault, and she starts yelling because she's like super excited. And Allie is over here sitting cross-legged. She's like chill. Okay. As Eliza runs away from Allie, Allie's going to hear a different frequency than what Eliza emits. So let's say that Eliza's frequency is go with 1350 hertz, and she's traveling with a speed of 7.2 meters per second. Question is that I would ask from something like that is, what frequency will Allie hear? Okay. And so we would go and start plugging information in based on that question. Is the frequency that was given 1350, is that F prime or is it F? That would be F because it's the frequency emitted by the source. So that means we're looking for F prime, which is what's observed. So F prime would equal 1350 times the velocity of sound traveling through the air, which we assume is the medium that Eliza's running through, is 343. I'm going to make a decision about this plus or minus right now. Do I expect the frequency to go up or to go down as Eliza runs away from Allie? We should expect it to go down. As she runs away, these waves are going to get stretched out, okay, and get further apart because she's running away as she emits that sound. And so we're expecting things to go down, which means we will use the lower of the two signs. So we'll use a minus. Velocity OBS. This is the speed of the observer. Who's the observer? In this case, Allie is. Is Allie moving? No, she's sitting all chill. On the bottom, we again have 343. Which sign do I use now, the minus or the plus? Plus. We use the bottom sign. We always use the bottom sign. If we're doing one, we do both. So we do a plus here. And how fast is our source moving? 7.2. Yeah, what do you got?
If they're going away, is it always the minus on top?
Yeah, so if the gap is becoming larger, we expect the frequency to drop. If the gap between them is getting closer, smaller, because they're approaching each other, we expect to use the upper sign. Now the frequency goes. This is simply a calculation. I will tell you, be careful about the denominator. Make sure you evaluate that denominator either in its own set of parentheses or that you evaluate it before you do the division. If you try to type it in from left to right without recognizing that denominator needs another set of parentheses, it'll give you a wrong answer. So someone put it in the calculator, 1322. That sound about right? Roughly 1322 hertz is the frequency that would be observed by L. Okay? That's the kind of problem you would have. Whether I change the variable and have you look for f prime or f, those are all just algebraic things. In terms of the conceptual, which is what this class is about, you should be good there. Question number 2. Know how to convert sound level to intensity and reverse it. Now, in this class this year, I know we did a couple different versions of the equation, but the base formula is that beta, the sound level, is equal to 10 times the log of I divided by 10 to the negative 12. That's our base formula. I think in the formula sheet it probably says I naught for the 10 to the negative 12. Okay, that's what it has there. But that is the baseline of our human ear's ability to hear. Okay, and so if we take that, plug that in for I naught, this is what we're left with. It is the relationship between beta and intensity. Now in this example, this formula we have here, this is really the formula that's used to find beta, if you know the intensity. Does anybody on their formula sheet or somewhere handy have written down the intensity version of the equation? Because we rewrote it so we make it easier for ourselves. Beta minus 120, and all of that is divided by 10. So you have to keep in mind that this thing up here, beta minus 120 divided by 10, that's all the exponent. So you start with beta minus the 120, get a number, divide that by 10, then do 10 to that power. So that allows us to go from sound level to intensity, okay, and gives us both the back and forth if we use the two of these. So a really simple example I've used before, would be you have a firecracker that's going to go off, and it might have a sound level, a loudness of 83 dB. Okay. And the question I would ask is, what if, instead of 1, what if I had 3? And so I would ask you, what's the sound level on 3 of these firecrackers when they're done simultaneous? Yeah?
Why doesn't it, because we know this, why doesn't it go like times 3 more sound intensity than just like a little bit more?
Yeah, so that's a great question. And the answer is more complicated than you think. Has a little bit to do with the anatomy of the ear. Has a little bit to do with the way that sound waves interact with each other. Okay, because sound waves, they'll have interactions that are constructive and destructive, a lot of things going on. And sound level is the decibel level is a man-made creation to explain how loud something appears to be to our ears. Okay, it's not a scientific measurement. It's a mathematical like scale for loudness. The actual scientific measurement is the intensity. It's how much energy there is per square meter. That's a measurement that is scientific in nature. The sound level is about our recognition of its loudness, which is more of a biological value. And that's still scientific, but it's more of a like a temperature scale. We just threw it on there and said what makes sense in terms of what we experience. Does that
Yeah.
sort of answer your question, but doesn't answer your question? Ask it to your physics professor in college. Okay. Or ask me when we have more time to go into it. All right, so you have the sound level. This is the beta for 1, and I'm asking for the beta for 3. Okay, so for us to figure out the beta for 3, we have to remember all of the adjustments have to happen on the intensity side of things. So first thing you need to know is what's the intensity of your first situation. So I would start by finding I1, which will be 10 raised to the 83 minus 120 divided by 10. And so I type that into the calculator. Yep.
Do we have to multiply it by 10 because it's decibels?
No. That right here has to do with why there's a 10 in front of the log to begin with. So that's built into the formula so that we measure it on decibels, not bells. That's a great question. But no, the formula is built to operate in decibels. And so for our intensity, this should be a fairly small number, like a E-4 deal. So 1.995 E-4, that would be in watts per meter squared. But I need to now take that intensity and turn it into the intensity for 3 firecrackers. Okay? Those 3 firecrackers would have, in terms of energy output, 3 times the energy output of 1. That is the scientific conversion. So I'm going to times this by 3 to get the intensity level of 3 of these firecrackers, which will be 5.986 E-4 watts per meter squared. Well, now I need to convert that back into a sound level, into a beta, which we have a formula for doing. It's 10 times the log of my intensity, 5.986 E-4 divided by, okay, the way that we write 10 to the -12, we can either write 10 with the caret key -12, or it's 1 E-12. Because 10 to the -12 is not 10 E-12, it's 1 times 10 to the -12. And so you could write it that way if you want to use the scientific notation.
You said 10 raised.
So you could write 10 raised to the -12, or it's 1 E-12. They have the same meaning and same value. Get 87.8. dB, decibels. So that's an example of what the second question could look like, how it'd be structured, an example of that process. All right. Question number 3. I'm going to tell you, it's the ray diagram, but it's going to be a pretty straightforward one. It'll be a pretty simple one in terms of it's either going to be a single converging lens or a single diverging lens. So I'll just do a real simple. I'm going to do a real simple model. You guys should have these in your notes. I'm going to do a simple model of what they would look like. And I'm going to make a suggestion. There was the formula 1 over dO plus 1 over di equals 1 over f. You can actually take the measurements from the drawing on the test and use them for dO and for f and predict where you're supposed to land. If you know where you're supposed to end up, then you can predict where that arrow is going to line up and where everything should cross. But suffice to say, should look something like this. What's ray 1 supposed to do? Parallel to the focal point. Ray 2, the focal point to parallel. And ray 3 should be straight through the center, looking like that. Again, you should have models of these on your notes. I'm just trying to remind you, before you take your test, these are the kinds of things you're going to be asked to do. And then, of course, we always finish by drawing in the image, which in this case is inverted right there. And that's how we would finish a converging ray diagram. Now, if the object gets inside the focal length, we do have a little bit of a different behavior. It behaves more like the diverging lens, which is the second type of lens that we need to talk about.
So the top one's converging.
Yep. Top one's converging because it's fat in the middle. Second one diverging because it's skinny in the middle. All right. What is ray 1 supposed to do? It comes in parallel. Instead of heading towards our focal point, it heads away from the first focal point. Meaning it does that. Understanding that because we're talking the diverging lens, it diverges away from the focal point. Second one, it can't aim at the close focal point because we just used that focal point. So it's going to aim as if it was going to make it to the second focal point, but it'll come out parallel. And because it's coming out parallel, it can be backtracked. Like that. Imagine that it's all one line. Like that. That's where our intersection is going to happen. Those two dotted lines cross back here. That's where we're going to end up with our intersection. Finalize the third one, always goes straight through the center. Like that. And our little guy right there is where our image is going to appear. On the test, I've got it pre-drawn in, pre-copies, so it's all set up for you. You just have to be able to use a ruler, go through that ray diagram correctly. any questions. I would really stress and encourage you. We did a day where we did on the notes, we drew all the different ray diagrams. I'd encourage you to have those handy, have them as a tool and a resource. Okay, question number 4. Snell's Law, okay, which is where we're going, light is passing from one material, one medium to another. So this might be glass to water, something like that. I have a ray of light coming in like this. I'm going to try really hard not to try and trick anybody right here. I'm just going to go ahead and draw this line in and call this a 20-degree angle. Now, you're either going to have to be given the what are called indices of refraction for the materials, or they'll have to be something you can look up in the book real quickly. I'm going to go ahead and use a glass of 1.52. I know that's one that gets used fairly often in the book. And for water, it's 1.33. Air, we use a value of 1. So first question I have is the light going to speed up or slow down? It's getting closer to having nothing in the way. Think about an N of 1 is a vacuum. So it'll go faster as it gets a lower index of refraction. Because it's speeding up, will it go towards the surface or away from the surface? Here's the trick that I always used to remember. Okay, you have to think about total internal reflection. Total internal reflection occurs when it bends so much that it stays inside, right? And so you have to think to yourself, when is total internal reflection possible? Now, Graydon and his group did the light through the water. The light will stay in the water and total internally reflect when surrounded by air. So that means it has a 1.3 going into a 1.0 total internal reflection. That means that if I'm going from a big number to a small number, I'm going to bend towards total internal reflection. Total internal reflection will be bouncing back inside the glass, but it tells me that generally I should expect this to bend with a bigger theta 2. The theta 2 should get bigger. I should be closer to the surface. Now, I'm going to tell you up front, I don't know what I drew when I did this question. It wouldn't surprise me if I gave you the complement angle and didn't give you the angle you need. That's the kind of nasty tricks I play, because it's something that was burned into my memory when I made those mistakes. So really emphasizing we go against perpendicular to the surface, not the surface. Snell's Law, N1 sine of theta 1 equals N2 sine theta 2. N1, our first material, is 1.52 times the sine of our theta 1 would be 20 degrees. Should equal 1.33 times the sine theta 2. It's a pretty straightforward calculation. And we divide by our coefficient and we take a sine inverse. Do make sure that your calculator is in which mode? Degree mode. All right, so again, evaluate that left side, divide by 1.33. Yep.
What page is
The indices of refraction. Numbers off the top of my head. Does anybody write it down on their formula sheet? Where N was, and we're doing C equals 642. Yeah, 642. 642 of your index of refraction. What do we get? Negative sign inverse. 23. 23.0. So theta 2 is 23.0 degrees. And I have your answer. Okay. Again, the Snell's Law stuff, pretty easy calculation, but it's the context. Okay. Physics is not just about can you plug stuff in your calculator. Can you interpret and evaluate context and apply principles of physics to it? All right. Question number 5. Be able to calculate the percentage of light intensity that passes through a series of polarizers. So we did this not too long ago. It was in chapter 24, where we said you have a Polaroid, light comes through it, 50% will make it through the first Polaroid. So if I only give you one, it's a really simple question, 50%. But if I give you another Polaroid that's been rotated by some angle, and maybe I do another one that's been rotated by some angle, okay? You need to be able to calculate the intensity. The intensity of the light that passes through is the initial intensity times the cosine squared of theta. Now, that is the formula, but it's a formula that has a lot of context buried inside. Okay? It is asking you to understand and interpret some specific things. The I naught will never be the total amount of light. Okay? It'll be 50% of the total amount of light, and then whatever comes through becomes the initial intensity for the next polarizer. So you have to understand the context of that layering. So let's just give ourselves some numbers. Let's say this is 30 degrees and that this is 20 degrees of rotation. Okay. The way I like to do this, to make my life easy, is I will call this I1. I'm going to call this I2, I3, and I4. The reason I do it that way is just so I can identify which point of time am I talking about. Okay, so I don't know what the initial amount of light is, and I'm probably not going to tell you an initial value, because it doesn't matter, it's about percentages. And so I2 is equal to 0.5 I1. I know that. So right here, what I'm going to do is replace I2 with 0.5 I1. Every stage, I'm going to replace I3 or I4 with a new value. That's what I'm trying to calculate. So to figure out I3, it will equal I2 times the cosine squared of theta. This is what I mean by before and after, right? So I3 will equal, what do I use for I2? I'm going to use 0.5 I1 times the cosine squared of 30 degrees. You can put the 0.5 and the cosine squared of 30 all into the calculator and evaluate without ever worrying about what I1 actually is. And if it really makes you like irritated to have the I1 floating around, you don't like that abstract nature, go ahead and give yourself an I1 value. What would be a convenient value for I1? 1. Because then whatever number gets out at the end of it, that's your decimal or your percentage of light that passes through. What is 0.5 times the cosine squared of 30? 0.375. What's that? 0.375. 0.375. Okay, so now I3, I now know that it's 0.375 of I1. I'm going to do the exact same calculation for I4. I4 will equal I3, but I3 is my 0.375. I1 times the cosine squared of second rotation is just 20 degrees. Again, I can plug in the 0.375 and the cosine squared of 20. get that I4, or the total light that passes through, is what decimal of I1? 0.331, or roughly 33.1%. I will take either of those as an answer. That's the kind of calculation we would make. Okay. Any questions on the first 5? Okay. When you guys watch this video at home, if you go back and you want to watch it or go through some of the stuff, what do you do when the video is 60 minutes long? You're like, this is the worst.
You watch it all.
Just fast forward. Find your way through it. All right. Actually, you know what we're going to do? We're going to